All right, so thank you for coming, everyone. Today we have Anna Weigandt, who will be talking to us about alternating sign matrices in Schubert calculus. Before we begin, just a reminder that we have a community statement. The three main points are we are all learning, everyone has something to contribute, and no one has all the answers. So please keep that in mind during the talk. So go ahead.
Great. Thank you so much for having me here. It's exciting to get to share some of my favorite combinatorial objects with you. They're sort of ubiquitous in combinatorics in that they have a habit of popping up in unexpected ways in a lot of different contexts. So I want to kind of survey some of the ways that these objects show up and give particular focus to some ways that they've shown up in my area of combinatorics, which is Schubert calculus. Okay, so first of all, the basic object, alternating sign matrices. So they're just square matrices with entries in -1, 0, 1, so that within rows and columns, the entries sum to 1. And then the alternating part is that non-zero entries in each row and column alternate in sign. So these conditions together kind of mean that you have to start in any row or column, like with a 1 is going to be the first non-zero entry you see. And then like maybe you're done, or maybe you find a -1 and then you like alternate back to a 1 eventually. So here's just an example of a 4x4 ASM. For n equals 3, I just drew out all of the different alternating sign matrices. You'll notice a lot of them are just permutation matrices. So they're just matrices with zeros and ones. But then in this case, there's one special one that's not a permutation matrix. So it's kind of, in a sense, these matrices are generalizing permutations. They contain permutations as a subset under the identification of a permutation with its permutation matrix. So one of the original reasons that people started thinking about these matrices was coming out of this recursive way of computing determinants called Dodgson condensation. So Robbins and Rumsey, they were studying this Dodgson condensation named for Charles Dodgson, who you might know better as Lewis Carroll, author of the Alice in Wonderland books. But anyways, he was a mathematician and he was studying some good stuff about determinants. So this method of computing determinants, what you do is you kind of, I drew maybe some colored guides to help us understand what's going on. So I'm not going to write out like definition, but the picture you should keep in mind is we kind of look at these maximal n-1 by n-1 submatrices. And so we can take one in like the north west. We can like multiply it by the one in the southeast. We subtract off what we get from these other corners. So we have like reduced this to computing some smaller determinants. And then we also have to divide by the determinant of like the interior stuff. And so we can do one round of this, and then for each of these other determinants, we could keep going and keep recursively doing this sort of procedure and somehow compute the determinant in the end. You have to be a little careful because for this recursive thing to work, you need the determinant of this interior matrix to be non-vanishing. So certain matrices, like you either have to tweak them around a little bit or do something slightly different, like do some row operations to be able to use this method. But this is the idea of what this looks like. So they were interested in this recurrence for determinants. And what they did was they deformed it slightly. They said, well, we can study something a little bit more general, and we might as well. We can throw a little parameter in there. So instead of doing a minus this, we can put a plus lambda times this stuff. And they called this the lambda determinant. And so, of course, when we plug in lambda equals -1, then we get back to the original recurrence that we had. So great. Robbins and Rumsey, they realized that alternating sign matrices could be used to take the recurrence out of this situation. So their theorem was that the lambda determinant of a matrix can be expressed as a sum over alternating sign matrices, where we take lambda to some statistic on ASMs, which is called the inversion number. Then we take 1 plus lambda to the number of -1s in the ASM. And then we take this funny like product, so overall ij, where we take the ij entry of m and we raise it to the bij power. And so this bij power, what's really going on here is that like for permutation matrices, we're just seeing kind of our usual sort of formula for determinant, but then there's like extra stuff with ASMs, and we have to be a little careful if we have negative entries in our ASM. We really need like this corresponding entry of the matrix to be non-zero. So again, there's a little bit of fussiness, but we can talk in like generic terms, and this works for most matrices you would encounter. Okay, what is this inversion number? It's just, you kind of look at the zeros in your matrix, and if they have like the first non-zero entry next to them to the right is a 1, and below them in the same column is also a 1, then that's like an inversion. You just count how many of those you get, and it generalizes normal inversions in a permutation in some sense. Okay. Are there any questions so far? Okay, so just summarizing some of the upshots of this formula. They took something recursive, they got something non-recursive. When you plug in lambda equals -1, so this again recovers the ordinary determinant, and you'll notice that all the non-permutation terms go away because the permutation matrices are exactly the matrices that have 0 -1s. So plugging in lambda equals -1 just really turns into the ordinary one way to define the determinant of a matrix as a sum over permutations, where you're taking like the sign of the permutation and multiplying it by this. You pick out the right entries according to the permutation from the matrix. Okay. If you have a matrix of all ones, there's a really nice formula for the lambda determinant that Robbins and Rumsey found. It's just simply you take 1 plus lambda and raise it to the n choose 2 power. And something that people have gotten a lot of traction out of studying is a specific case when lambda equals 1, they gave combinatorial interpretations to what is called the 2 enumeration of ASMs. So in plain terms, you're summing over all ASMs, and the weight an ASM gets is 2 raised to the number of -1s in the matrix. Okay, so this was some of the original motivation for Robbins and Rumsey to be studying these matrices. They were the right matrices to help them understand lambda determinants. But they became interested in sort of a related enumerative sort of statement about alternating sign matrices. In combinatorics, very often we like to count things. And so one can ask, well, how many alternating sign matrices are there? So let's gather some data. I've drawn out n equals 1, n equals 2, n equals 3 we've seen before. I'll start to run out of space fast, so you can trust me that n equals 4 is 42, and then we continue on in this way. And looking at this sequence, like, I don't know, it might not be immediately apparent to spot a pattern, but Mills, Robbins, and Rumsey did spot a pattern. So in 1982, they conjectured this very explicit product formula for the number of alternating sign matrices. So it's just a simple product of a quotient of some factorials, where we're taking our indexing set going from j equals 0 to n minus 1. So this like simple looking formula generated a lot of interest in the combinatorial community. And people spent about a decade trying to prove this in earnest, and like discovering more things about alternating sign matrices along the way, but not quite getting the enumerative proof. And so this remained open until Zeilberger gave a proof in 1992. This proof was a massive undertaking. If you look at the paper, it's many pages long. It has lemma, sublemma, sublemma, and so on. And these lemmas were like outsourced to various mathematicians in the community to check. So this was such a highly technical piece of work that like they really wanted to be sure that this conjecture was really proved. And so it went through a lot of checks and was verified and accepted. Then a few years later, Kuperberg gave a very short proof using techniques from statistical physics. So he was able to connect alternating sign matrices to this whole other world and use the techniques from that world to ultimately get at this enumeration in a very different way. Okay. So there's some other sets of objects. There's a lot of set of objects that are enumerated by the same formula. Some of the like famous ones are these things called descending plane partitions and totally symmetric self-complementary plane partitions. So they are known to have the same enumerative formula as ASMs. Provably, people have counted the numbers of these objects. And in combinatorics, whenever we know that we have two sets that have the same count, like theoretically they're in bijection, but we want to find an explicit bijection that would give us a combinatorial proof that they're the same, or a combinatorial explanation for why these things have the same count. But we don't know any of these bijections still. There's just, yeah, we know that they should be in bijection. We even have like refined enumeration and results saying, okay, there's this statistic on ASM and the like statistic distribution matches the statistics on descending plane partitions, but still in general, there's not been any way to just line them up in a bijective sort of way. So whenever we're missing this bijective explanation, it's very intriguing in combinatorics, and again, has generated a whole lot of interest in studying these three families of objects and what links we can find between them. So just to flash a picture, here's what totally self-complementary symmetric plane partitions look like. I probably permuted the adjectives a little bit, but the idea is that you have like some plane partitions, so you're stacking some boxes, and this totally symmetric means you can kind of like rotate it along these axes and they stay the same. The complementary means that if you complement in the cube, you get the same plane partition. So it's a lot of like restrictions on these plane partitions. But here we have 7, and these are the sort of n=3 objects. Descending plane partitions, I don't have as nice of a picture, and I've given some like indices, rules, things. Here's the ones for like n=3. But maybe let's not linger too much on what these rules are, but just you can explicitly write down these objects. And again, there's 7. And why should that 7 be the same as the ASM and the totally self-complementary symmetric plane partition thing? Okay, but there's also a lot of like less mysterious bijections. There's many different types of combinatorial objects that have bijections with ASMs. A nice survey of a lot of these different bijections is James Propp's The Many Faces of Alternating Sign Matrices. Just a short article where you get a lot of different objects and explanations of how they're in bijection with ASMs. So I took a couple of pictures from his survey. So these things are like fully packed loop configurations. This is like the gasket and basket model for ASMs. So just a bunch of different pictures, different objects with different sorts of properties that you can find nice bijections between them. And this is sort of pointing towards, again, a major theme that ASMs are kind of like ubiquitous. They have a habit of popping up in different looking guises, but they're essentially the same fundamental object. Okay, so one of these very important guises, the one that Kuperberg so successfully enumerated ASMs using these objects, is the 6-vertex model. So what's going on with the 6-vertex model? It starts with motivation from physics, and we're trying to model what water looks like when it freezes and turns into ice. So ice is made up of a bunch of H2O molecules. So we have 2 hydrogens and an oxygen. And an ice model tries to explain how these pieces fit together when water freezes. And the 6-vertex model, it's a 2-dimensional sort of simplification of this scenario because, well, 3D things are hard, 2D is a little bit easier to deal with. And when our ice freezes, we're assuming that our molecules kind of arrange themselves into these rigid configurations that you see here, 6 different types of these configurations. So we can then try to see how can we piece these together to get a square sheet of ice. So here's one such example of we have kind of a fixed grid of where our hydrogens and oxygens are going to end up, but then we want to draw in these sort of bonding things to make our molecules so that our hydrogens are adjacent to some oxygens and so on and so forth. So I personally find these sort of pictures a little bit harder for me to draw. And like the statistical physics people, they kind of distilled this information into a different picture. So kind of like tile by tile, building block by building block, they rearranged this into something called the 6-vertex model. So you have sort of these boundary vertices where the edges on the outside here and here, they point inwards, but the top and bottom boundary edges point outwards. But then you're free to orient things around the interior vertices in all sorts of ways with a given rule that at any interior vertex, you must have 2 arrows going in and 2 arrows going out. So if you need to have 2 in and 2 out, this gives you 6 total possibilities at any interior vertex. So this is often called the 6-vertex model. So we can just line up our sort of molecule configurations with our interior vertices like so. Okay. But I even like to draw this a different way because there's too many arrows. And so I tend to like to draw it in this way, where I can just look at the arrows that are pointing left. And then if the arrows are pointing right, I don't need to pay attention to them because I've already highlighted which arrows are pointing left. And same with the arrows pointing down, I can just focus on those and then know if I didn't highlight them, they were pointing upwards. And so when we do this, we get, again, a tile by tile sort of mapping to give us this sort of object here, where now I'm just kind of drawing some squiggles instead of drawing so many arrows. And you'll notice that these boundary conditions kind of mean that we have to start kind of over here on the bottom. We have to end on the right. We can't have anything sticking out of the left edge or the top edge. And we have n total little strands in our picture if we have an n by n grid. So these things actually showed up independently in Schubert calculus world in work of Lamley and Shimizono, and they called them bumpless pipe dreams. So a bumpless pipe dream is just a tiling of the n by n grid with these tiles so that pipes start at the bottom of the grid and end at the right. So we're thinking about these little strands as being just like pipes that are carrying water around our picture. The word bumpless, it won't be very relevant to us yet, but in Schubert calculus world, they draw other pictures that look kind of like these, and they like to have these bumpy looking tiles. So they said, Lamley and Shimizono said bumpless to really indicate that these are different sort of pictures from the ones that had been around before. No bumps allowed. Okay. What does this all have to do with alternating sign matrices? Well, there's a simple bijection from these pictures, so states the 6-vertex model or bumpless pipe dreams, to alternating sign matrices. And the map is really simple. If you have a little hook that goes like this, then you put a 1 in the corresponding entry of the matrix. If you have this little upward hook, then you put a -1. And all the other entries turn into zeros. So this direction of the map is kind of clear, and you can check well-definedness. It follows kind of from the way the pipes are flowing. The inverse direction is also not so bad, but maybe a little bit fussier. But we'll just assert fact, this map is a bijection. So I've written out the 7 bumpless pipe dreams and the 7 ASMs that they go with. So once you know the ASM, you can put in the appropriate upward and downward hooks, and then there's kind of a unique way to follow the rule for them, for you to fill out these pictures. Okay. All right, so I kept saying like these ASMs, they show up in Schubert calculus, but so far we haven't really said like what is Schubert calculus. So I won't go in depth, but I do want to just give you like a little overview of kind of the motivation, the world that these problems are living in. So Schubert calculus, it grew out of enumerative questions asked by Hermann Schubert and his contemporaries in the late 1800s and early 1900s. So they were asking lots of questions about how various objects sat in space together. And one famous question, and the one that if you meet any Schubert calculator, they'll probably tell you first because it's the nicest one to visualize, how many lines meet 4 fixed lines in 3 space? So if I just fix 4 lines at random, you can ask how many lines meet all 4 of those fixed ones. And if you're just trying to like picture these laser beams in space, it gets a little bit challenging. And so what like Schubert did was he said, okay, let's go ahead and make it like a little bit more special. So instead of having like 4 random lines in space, let's take 2 of them and we'll make them sort of drag them in space until they intersect. And then let's take the other 2 and drag them in space until they intersect. And now's the part where I check if you're still out there in the Zoom void. Now that I've like rearranged these things a little bit and made the situation a little bit more special, can anyone find me a line that meets all 4 of these fixed lines? Either in the chat or you unmute or gotta see if you're still out there.
Is it just the one that goes through both intersections?
Yeah, that's a great line. Yeah, we have 2 points and through 2 points there's a line. I'm not going to be able to smoothly change my color on this. So unfortunately the new line is also going to be red. Okay, so we have that line that's meeting the intersections. And then there's a trickier line. And if you've been TAing a lot of Calculus 3, you might be more primed to find this trickier line. But if you have 2 intersecting lines, they span a plane. And if you have 2 planes, they intersect in a line. And so if everything is like sufficiently random, you can expect that these 2 planes, oh goodness, are going to meet kind of in a line that's going to meet all 4 of the fixed lines. So this was the sort of argument that Schubert used, that you can kind of make things a little special. And then he said, by the principle of conservation of number, you can sort of drag things back into their original position. And as you carefully drag things back, you end up with the same number of solutions. So in this example, the answer is actually like 2. We found them all. I won't argue why we found them all, but yeah. So they were looking at enumerative problems like this, but then Hilbert kind of came along and was like, hey, like this principle of conservation of number, it's not very precise, the way you're like squiggling things around through space. And like some enumerative geometers were getting different answers for the same problem, which isn't good. So Hilbert, when he posed his list of problems at the turn of the century, one of them was about Schubert calculus and making it rigorous. And the way it was made rigorous was through the development of things like cohomology and intersection theory, coming up with these tools in algebraic geometry to make these computations that Schubert was doing more precise. Okay, so what does this look like in modern terms? So in modern terms, the type of Schubert calculus that I tend to study has to do with this thing called the complete flag variety. So this is the general linear group modded out by like the spiral subgroup of upper triangular matrices, but whatever, some geometric space. And inside of this space, there's these special subvarieties called Schubert varieties. And then to the complete flag variety, we associate some sort of gadget called cohomology. And each Schubert variety gives us a Schubert class. And cohomology, if it's not a gadget that you're used to thinking about, just know that it's some ring. and the ring can tell us some information about the geometric setup of this space. And then the Schubert classes, they form a basis of this ring. And if you really don't want to think about like cohomology rings geometrically, thanks to Borel, there's an isomorphism which presents this ring as a quotient of a polynomial ring. And so the idea is that we can take these Schubert classes, and instead of trying to do like cup products of Schubert classes, we can multiply polynomials instead. And then we're just doing our multiplication up to some ideal that's generated by elementary symmetric polynomials, the non-constant ones. Okay, so Lascaux and Schutz and Berger, they proposed a choice of coset representatives for the Schubert classes, and they called these things Schubert polynomials. And their initial definition, it was recursive using these things called divided difference operators, and subsequent work on Schubert polynomials led to this big combinatorial theory that studies the polynomials and combinatorial formulas for them, with a particular interest, of course, in trying to understand combinatorial ways to multiply them, going back to the original motivation of understanding the cohomology ring of the flag variety combinatorially. So we'll talk today about two formulas for Schubert polynomials, and the first one uses bumpless pipe dreams, which again are just alternating sign matrices in disguise. So first we need an extra little definition for bumpless pipe dreams. A bumpless pipe dream is reduced if any pair of pipes crosses at most one time. So here I've drawn a non-example where we have this pipe kind of crosses and then it crosses back, and this thing is not reduced. But if we take just reduced pipe dreams, we can use them to write down these Schubert polynomials. So we first need to get a permutation out of these objects. So what we do is we just label the bottom pipes from left to right with the numbers 1 through n, and then we just trace where the pipes go. So for instance, like this one, I like, yeah, okay. I guess I'll just go to this slide, which maybe has too much information, but this one, I sort of trace along here and it pops out up here. So I write a 1. The 2 I trace and I write a 2, and so on. And so what I get is a permutation written in one-line notation, this permutation 1, 4, 3, 2, 5. And then I also get a weight by looking at these boxes that didn't get struck out by any of these pipes. And these boxes are actually just secretly the positions of the inversions that we saw before. So I weight them according to what row they're in, and then I multiply together these things to get a weight for my object. So now at this point, I'm in a pretty good position to write down a formula. And the formula of Lamley-Chamizono is that the Schubert polynomial is this weighted sum over reduced bumpless pipe dreams that trace out your permutation W. So these Schubert polynomials, they're indexed by permutations. We collect all the reduced bumpless pipe dreams that go with the same permutation, and we add up their weights. Okay, so this was a newer formula for Schubert polynomials. Oh, this is just to say that there's a way that we can generate all the bumpless pipe dreams for a given permutation by doing these little droop moves. So a very algorithmic way of gathering together all the bumpless pipe dreams that go with a fixed permutation. There's another formula for Schubert polynomials in terms of pipe dreams. So these are the ones that have these bumps now. And on the main antidiagonal, we just always put this sort of upward bump. Above the main antidiagonal, we're allowed to sort of freely pick these bumping tiles or these crossing tiles. And below the main antidiagonal, we just leave all this empty space. And so we trace out a permutation in a very similar sort of way. We have a similar definition for reduced, meaning pairwise pipes cross at most once. And then we weight these in a slightly different way. Instead of looking at the blank tiles, which are just always exactly the same for every pipe dream, we look at the crossings. And we record how many crossings happen in row I, and that gives us the exponent of xi. And so we can now collect all the pipe dreams for a fixed permutation. And here I'm putting like a lot of people, like maybe I should add a Billy Jackish Stanley. There was sort of a bunch of work all at once that saw this formula in equivalent combinatorial ways. I'm saying Fomin, Krylov, and Bergeron Billy because they really were closest to this picture that you're seeing. But the Schubert polynomial is a weighted sum over reduced pipe dreams that trace out W. Okay, and again, there's some sort of algorithmic way due to Bergeron and Billy of starting from a particular pipe dream and generating the rest of the pipe dreams for your permutation. So you can think in a combinatorial sort of way about these objects. Okay, so looking at these two formulas, they're giving us formulas for the same polynomial. Each object is contributing a single monomial. So there ought to be a way to line these up. And this is kind of like our enumerative thing from the beginning. We're getting the same count in two different ways. We ought to be able to line things up in a way that explains this. And indeed, there was a weight preserving bijection given by Gao and Huang. And they even showed like, if you have a bijection that's respecting the multiplicative structure of Schubert polynomials, this is like the unique bijection that does that, the one that they gave. In this example, I lined things up in the only way one can. So that the BPD on the bottom has the same weight as the pipe dream on the top. But there's these more complicated looking, more detailed versions of Schubert polynomials where instead of just having x's, you have x's and y's. So these are telling you geometrically about some gadget called torus equivariant cohomology. If you set the y's all equal to 0, you just land back to the normal x's. So it's just giving you strictly more information about the geometry than you had before. And if you try to just line things up with this sort of x's and y's version, well, now you're trying to line up these products of binomials. And even though they're going to expand to both be the double Schubert polynomial, they're like, you just can't line up object by object with each other to get a bijection that preserves these binomials. So there's something very combinatorially different. Here the x's are meant to be tracking row information still, but the y's are additionally tracking information of columns. So this is just like, yeah, a little bit mysterious when you try to deal with x's and y's at the same time. It becomes a more difficult sort of situation. Okay, so now we're going to move on to a generalization of Schubert polynomials called Grothendieck polynomials. And we're going to see how maybe bumpless pipe dreams were like hiding in the literature in a formula that was known about Grothendieck polynomials already. So in this unpublished preprint from 2002, Lascu gave a formula for Grothendieck polynomials. So these generalizations of Schubert polynomials in terms of alternating sign matrices. And I translated Lascu's work and filled in some details to give a bumpless pipe dream formula for Grothendieck polynomials. So you read out like the permutation in a slightly more subtle way for these K-theoretic formulas for Grothendieck polynomials. If pipes cross twice, you want to kind of ignore any subsequent crossings. So you have to like add in little extra bumps to get the right permutation. And then the weight is also a little bit more funny, kind of in the sense where you're taking like these, I called this I of P before, sorry, but D of P, I of P, these blank tiles. And then we have like also a product over these sort of upward tiles, which were the negative ones from before. And we get like this zoo of a thing called a K-theoretic weight for our object. So anyways, this formula probably won't land on this slide, so I'm just going to show it to you so you realize there's a little bit of extra complexity, but then it reduces back down to the formula that Lamley-Shimizono gave. So you have kind of these similar terms from before. And then here you have this extra non-reduced term. But if you just take lowest degree terms, you get back to the Schubert polynomial situation. Okay, so one thing that you kind of get out of this situation is you can recover this 2 enumeration formula for ASMs, where we take this lambda determinant thing, we plug in lambda equals 1. You can get it in like a cheap way, but a silly way by Schubert calculus. So what's going on here is we're taking our Grothendieck polynomials and we're setting xi to be -1. And then we're going to kind of like normalize somehow. So we're getting all positive stuff. And so we get a 2 enumeration weight for our objects here. In other words, the weight is just 2 raised to the number of -1s that you see in your matrix. And then there's a different pipe dream formula for Grothendieck polynomials, where each pipe dream is contributing exactly 1 monomial to a Grothendieck polynomial. And the idea is that n by n pipe dreams are in bijection with subsets of this triangular grid. In other words, there's 2 to the n choose 2 of them. So 2 to the n choose 2 is equal to a sum over pipe dreams, which is equal to this specialization of Grothendieck polynomials, which is equal to this 2 enumeration of ASMs. So this is like maybe overkill for what the statement is, but just inside of Schubert calculus land was hiding some information about 2 enumerations of ASMs. Okay. And then this is just showing like, here's our sort of bumpless pipe dream row and the corresponding ASMs. Here's all of our pipe dreams. And then here, this one is counting for like 2 things, basically. So this 1 bumpless pipe dream ought to go with 2 pipe dreams. Okay. So that was one way that bumpless pipe dreams, or in particular ASMs, were hiding in Schubert calculus world and had been hiding there since 2002. And another way that they're important is they have this tie to something called the Bruhat order on the symmetric group. So what we can do is we can take alternating sign matrices and we can give them a poset structure. So we're going to define this corner sum function on ASMs. It's kind of what it sounds like. We take these maximal submatrices starting at position 1, 1, and then in the corresponding bottom corner, we just sum up the entries that we boxed together. So here 0 plus 1 plus 1 plus -1 gives us that 1 that I've boxed in on the corner sum function. So we can order these corner sum matrices by entry-wise comparison. And we're going to do a funny little thing. We're going to say that A is greater than or equal to B if and only if the corner sum of A is less than or equal to the corner sum of B. Again, entry-wise. This is just for reasons. So when we do this, we get this poset here. So up here, this is going to be like the biggest one. Most of them look like permutations. And then there's this special middle one that's an ASM that's not a permutation. And if we forget about that one and take the induced subposet that we get this strong Bruhat order on the symmetric group. And so the strong Bruhat order, it can be defined in a lot of different ways. It can be defined, for instance, in terms of covering relations where you're swapping entries in the string and going up by 1 in Coxeter length as you do so. But anyways, the ASM poset is containing the strong Bruhat order as a subposet. And in fact, it's the smallest lattice that does that. So ASMs are a nice lattice, which means they have a lot of good structure, and they sort of complete the strong Bruhat order on the symmetric group. Okay, so going back to sort of Schubert calculus land, we can define these things called alternating sign matrix varieties, where we're taking as our ambient space, the space of n by n matrices, and we're looking at just the matrices whose rank of the first I rows and j columns is less than or equal to that value in the corner sum matrix for all positions. So if we look at this example here, there's a lot of sort of vacuous rank conditions. Like this is saying that a 2x1 matrix has rank at most 1. Like, okay, that's a given. And like a bunch of vacuous conditions. But then we have a couple of conditions that are actually like non-trivial here. And so what we can do is we can start working out what these conditions are telling us. If we take kind of a generic matrix here, this rank 0 means that the top 1x1 matrix has to be rank at most 0, which tells us that this entry has to be 0. This being rank at most 1 tells us that this submatrix has to, well, have a vanishing determinant. And so we can like compute this determinant, we get 0 when that's what it means to vanish. And then this sort of term goes away. And we really get down to this condition that B12 equals 0 or B21 equals 0. And so this kind of, we can puzzle apart what this sort of variety looks like by analyzing these rank conditions. But there's also ways to think about them in terms of this poset of ASMs. So we can let perm of A be the set of minimal permutations that live above A in the poset. So here, if you're a permutation, your perm set is just yourself. But if you're an ASM, like here, I've highlighted the permutations that are minimally above this, this alternating sign matrix. And it's a fact that the alternating sign matrix is just a union over the permutations in its perm set of these other ASM varieties, which are technically, Fulton defined them and studied them and called them matrix Schubert varieties. So when you're indexed by a permutation, you are just like, you are a matrix Schubert variety, a nice irreducible variety. So in this example here, we were really getting that we had a union of these two different matrix Schubert varieties that were defined by these different conditions. Okay, so what we can do with these things is we can kind of, we can see bumpless pipe dreams hiding in another way in deep inside of the geometry. So we can start with like our Schubert determinantal ideals, which are sort of the ideal version of the alternating sign matrix variety. And we like get some rank conditions, and there's some most important ones, but here I'm just kind of flashing a picture. And the matrix Schubert variety has like another interpretation here. And so this matrix Schubert variety, we can think about taking this Schubert variety that we met before that's living down in the flag variety, and we can kind of pull it back along this projection map from the general linear group to GLN mod B, and then we can include it into the space of n by n matrices. And when we take its closure, this gives us Fulton's matrix Schubert variety, which we defined before in terms of these explicit rank conditions. So looking here, we can take our matrix Schubert variety, and then we can do what's called a Grobner degeneration, which means that we can degenerate it to its initial ideal. And so normally we have to be like a little bit careful, and we have to like compute a Grobner basis and then like take the lead terms of that Grobner basis, and this thing is going to generate our ideal. But lucky for us in this example, the given generators are already a Grobner basis. And what we're going to do is we're going to fix a particular term order where we're just going to say that Z11 is sort of the best thing, then Z12, and so on. So when we fix this term order, our initial ideal is going to be this intersection here where we have kind of, we take this lead term, here's sort of the lead term that matters, and then we're going to take a prime decomposition of this thing. And so when we do this, we get this. And if you're not happy taking prime decompositions, that's fine, but I just want to get to this picture. And what we see here is that the bumpless pipe dreams that we saw before for this permutation, their blank tiles are telling us exactly the list of variables that we're seeing in our primes for the initial ideal. And even this sort of doubled version is telling us the X and Y values of this. So this is giving a geometric explanation for the combinatorial formula that we were seeing. And this is my theorem with Patricia Klein, that if you take any intersection of Schubert determinantal ideals that have the same height, or in other words, the matrix Schubert varieties have the same codimension, then when you take this initial ideal, you might get something that's like not radical, and that's okay, ignore that, but you get some components with some sort of funny multiplicities, and the bumpless pipe dreams for the permutations in this list are going to give you sort of the primes with multiplicity in this degeneration. So let's just like puzzle through what this looks like with a really tiny example. So I'm going to take an intersection of these two Schubert determinantal ideals. And then over here, this one is just very simple. Over here, this one has a little more substance. I take the intersection. I actually just get like a hypersurface, and then, or just like a single generator. And when I take the lead term with respect to this diagonal term order, then I get this sort of initial ideal here. So this thing is like not reduced because we have this Z11 squared, which is kind of a bummer. Or it's not radical because of this Z11 squared, but that's okay. We can take a primary decomposition. And here, this exponent of a 2 is kind of telling us that there ought to be 2 Z11s. And this Z22, there ought to be sort of one of them. And we see that this is reflected combinatorially when we list out the bumpless pipe dreams. So here we have 2 different bumpless pipe dreams for these permutations that have this Z11 box. And here we have another bumpless pipe dream for this different permutation 132 that has the Z22 box. So the moral of this story, it got like a little bit technical, but the big takeaway idea is that to understand these degenerations of these geometric spaces, we can use bumpless pipe dreams, which are also known as alternating sign matrices. So alternating sign matrices were somehow governing this geometric setup in the background. Just they were there, just waiting to be found. So not only are they kind of ubiquitous in combinatorial settings and popping up in lots of different ways, but they're also really governing this geometric situation. So yeah, that's about all I wanted to say. So thank you so much.
Thank you so much for the talk. Do we have any questions?
I have a question if nobody else has a question.
Hi, Anna.
Hi, very nice talk. So at some point you said that for the pipe dreams, you had like a term or several terms that then became 2 terms in the bumpless pipe dreams?
Yes. Yeah, so the weight, like the K-theoretic weight for the bumpless pipe dreams has each -1 counting for like the number of terms of an ASM is going to be like, sorry. So you take a bumpless pipe dream, you want to know how many monomials is it contributing to a Grothendieck polynomial, and that number is 2 to the number of -1s.
Yeah, so then if I look at your poset that you drew,
yeah,
so that middle vertex, if you made it sort of into 2 things,
yeah,
then it looks almost like a crystal graph.
oh, okay.
So I'm wondering whether there's like a way to sort of split apart that middle vertex.
Yeah. And there's really recent work of like Mark Shimazano, Daoji Huang, Tian Yu, where they give an explicit bijection between marked bumpless pipe dreams or marked ASMs and pipe dreams. And so I wonder if using their bijection to kind of split an ASM into multiple pipe dreams, if there would be something neat there to study in terms of crystallographs.
Okay. Yeah, thank you. So yeah, I can look at that paper. Yeah.
So you talked about the droop moves on bumpless. Does that correspond to like a nice thing on the ASMs?
Oh, yes. And initially, like where Lamley Shimizono, well, maybe they were thinking about droops ahead of time, but Lascaux on ASMs called it inflation. So like you were basically so taking a sort of situation where like this is going to this. In the ASM land, you have like a -1, which I tend to draw with open dots, and ones here. And then to go to kind of undroop, you're doing Lascaux's inflation procedure. But Lascaux's handles K-theory as well. So in my paper, I described like K-theoretic droops, which again is just translating what Lascaux did to this sort of more pipe way of thinking.
Okay, thanks.
Okay, so let me stop the recording. Oh,